Good morning, folks. It's Wednesday, April 15th. I hope everybody's struggling through this new reality as well as can be expected. You're staying safe and you're staying well. So today we're going to do a quick PowerPoint on transformers, and then we're going to transition straight into the problem solving on the smartboard with our calculations, circuit calculations for part 4, which will be concerned with step up and step down transformers. So it's pretty important that we learn a little bit about what we're dealing with before we move on to the actual calculation. So transformers. I'm going to start off talking a little bit about AC current and DC current. AC stands for alternating current, DC for direct current. And exactly what are they and what do they mean? Well, alternating current, much like the name says, the electron flow changes direction. So the electrons will start off at rest, speed up to a maximum speed, slow down, stop, turn around, go back up to a maximum speed, slow down, stop, turn around, up to a maximum speed, and so on, back and forth, back and forth. And in North America, our current does that 60 times a second. So in effect, our standard light bulb is going to blink on and off 60 times every second. So that's AC current. Direct current, well, that's kind of what we demonstrated yesterday when we were in yesterday's video. I described the electrons as leaving the negative electrode of the battery, traveling through the resistors, and then coming back around to the positive terminal. That's direct current. So why then, if we use an awful lot, most of our devices in our houses are actually DC, they use DC current and have to be converted to DC. Why is it that we deliver the electricity to your house, to the wall plug-ins, as AC? Exactly what is going on with that? So I started off by posing that as a question. Ever wonder why electricity is delivered as AC, alternating current, when most of our devices run off of DC, direct current? Well, it comes down to the transmission of electric current. So when we have a power plant generator down the road, like we do at Milner, when they produce electricity, if they didn't step up the voltage to a very, very high voltage, which reduces the current down to a very, very low current, then the higher current as it traveled through the wires, even just to get as far as Grand Cache, never mind to get to Calgary or to Lethbridge or to High River or anywhere else that they might be sending the electricity. As it travels through the wires, the resistance would be so high that the energy would be used up and lost as heat. So be heating the air around those wires very, very well, but we would not be getting electricity actually transmitted. So we have to step up the voltage very high, and by stepping up very high voltage, it steps down the current. So the very low current allows the electricity to travel through the wires. The resistance doesn't affect it then. We don't waste that energy as wasted heat energy. So until recently, only AC could be stepped up using transformers to high voltage needed to overcome the resistance in the transmission lines. So to overcome the resistance in transmission lines without losing energy during the transfer and the storage, because that grid, as they call it, the power grid, those wires that transport electricity throughout the province, they also store that electricity for us as it works out. So that's why we use AC. Apparently there are methods now to step down DC. You could do it on a small scale with just turning switches on and off, and so maybe electronically that's what it does, but the system is all set up around it being generating in AC. We're going to understand that a little better when we start looking at these transformers. So exactly what is a transformer? Here's an example of a step-up transformer, it tells us. So let's just look at some of the information which is on that slide. So we start off with 100 volts in the primary. So the primary is the incoming side of the transformer. It had 100 volts. It had 10 amps. Now you remember from calculations number 2, I believe, P equals IV. So I, 10, times V, 100, is equal to 1,000 watts. On the secondary side, you can see that the voltage has been stepped up, ergo the name step-up transformer, but the current has dropped down. But if you still multiply the 400 by the 2.5, the I times the V, 2.5, you still get 1,000. So that's conservation of energy. The power is going to be equal on both sides of a transformer always. Now look how you accomplish that. So in the primary, you have 5 turns. I'm going to continuously call those wraps in today's lesson, wraps and terms and turns and wraps. It's the same thing. So 5 turns, 5 wraps. It goes up to 20 in the secondary. So to change 5 into 20, we would multiply it by 4. Look what happened to the voltage. When we look at the voltage, went from 100 to 400. Again, it increased by a factor of 4. We multiplied 100 by 4. But look what happened to the current. Current went from 10 amps to 2.5. So in other words, we divided it by 4. So in each case, 5 to 20 multiplied by 4. Voltage to voltage multiplied by 4. Current to current divide by 4. Current is always going to be doing the opposite of what the number of wraps and the voltage do. The voltage and the wraps will always go up by the same amount, or in a step-down transformer, go down by the same amount. Current will do the opposite. If the wraps go up and the voltage goes up, the current goes down. So a transformer is also sometimes referred to as an induction coil. It's a device that's used to convert voltage to a higher or lower level. So exactly what are the parts of a transformer? So here's an old picture out of an old black and white workbook that we used to use in Physics 30 back in the good old days. And it shows that we've got an AC source sending current through this coil. So remember what that means. It means electricity is going this way, then it stops, and it goes back this way, and then it starts. It goes this way, it stops, it goes this way, back and forth and back and forth. So we put a number of turns around it. What we always used to use in the old days was a soft iron core. Modern transformers, they have other devices to do the same. But we've got this soft iron core, and the electricity doesn't get conducted to the secondary coil. What happens is, as this first starts up, the electricity starts going slow and gets faster and faster and faster. That causes a changing magnetic field in the primary coil. This changing magnetic field induces magnetic field around the secondary coil and causes electrons to go. That's the electromotor effect, the generator effect. So by having a changing field here, it produces a changing field here, which produces current. If this was a DC source, when you first turned the switch and turned it on, you would get one blast of electricity over here, then it would stop. This current would be running constantly at a constant speed, and there would be no changing magnetic field. There'd be a magnetic field, but it'd be constant. So no electricity would be generated. It's only because it's changing by going one direction, stopping, going the other direction, stopping, going this direction, stopping, back and forth, that creates a changing magnetic field. When that changing magnetic field induces electricity to flow through here. Don't really have to understand that for Science 30, but that kind of helps explain why it has to be an AC source. Or you can have a switch here turning on and off, on and off, on and off, and that would have the same effect. Of course, that's going to be very tedious and not work very well. So this, what type of transformer is this? We can count them 1 turn or 1 wrap, 2, 3 in the primary. In the secondary, 1, 2, 3, 4, 5. Maybe you got a 6th in there. More in the secondary, which means the wraps go up, the voltage goes up, the current goes down. It's a step-up transformer. So step-up transformers. Step-up transformers will increase the potential difference. They increase the voltage. They have a certain number of wraps in the primary, or a certain number of turns in the primary, and then they'll have more in the secondary. Well, why do we do that? We increase the voltage. There's different reasons for doing that, but generally speaking, in terms of electrical power plants like Milner, it's so that we decrease the current. So as we increase the current in a step-up transformer, increase the voltage in a step-up transformer, we always decrease the current and there will be more wraps in the secondary than the primary. So voltage increases, number of wraps increase, and current decreases. That can identify a step-up transformer for you. Step transformers are used to increase voltage at power plants before electricity is transported through what we call the power grid. Better name would be the energy grid, but that's okay. That's our common vernacular for that. So what's another really common example of a step-up transformer is a spark plug. A spark plug is actually a step-up transformer. So what we do is we take a certain number of wraps in the primary, more wraps in the secondary, increases the voltage so that it'll spark across and ignite your gasoline fumes. And your cylinder cause a minor explosion, drives the piston down, and off you go. So the step-up transformers are a common example is a spark plug that we see every day. So what about step-down transformers? Well, here's an example of a step-down transformer. You've got your soft iron core here. This one is rectangular. It could be circular as well. Remember, no electricity is transferred through that. It's simply the magnetic field here induces a changing magnetic field here and causes electrons to flow. So in this case, we have lots of wraps in the primary, lots of turns in the primary. We have less wraps or less turns in the secondary. That means the voltage is going to go down, but the current is going to go up. So why do we need a step-down transformer? It made sense. We had to step up the voltage to transfer it through the power lines. Well, that comes in at a very, very high voltage. As you probably realize, most of the potential difference, most of the voltage in your house when you plug in stuff is going to be 120 volts, except you'll have two outlets with 240 in your house, and those two are going to be the dryer down in your laundry room and the stove up in your kitchen. Now, in the United States, they actually use 110 instead of 120 usually, which is okay. All of our 120 devices can plug into a 110, or the 110 devices can plug into a 120, and they run very smoothly. But if you go up to Europe, they use a 240 volt system most of the time. So you have to be very careful about how you do your adapters when you travel overseas to other countries other than the United States. So a step down, when they talk about up and down, they're always talking about voltage. So a step down is going to decrease your voltage, but that means it's going to increase current. So why do we have to step it down? Well, we have to step it down to 120 because that's a starting point then for our electric devices. You can't use it at the many, many thousands of volts that it comes in at. So the first step down transformer in your community will be on the edge of the town. So transfers, you're going to have one step down. Then when it gets to your neighborhood, it's going to be another step down. And then when it gets to the back of your house, it'll have another step down. Back in Manitoba where I worked, we lived on acreage as a farming community. Everybody point out their step down transformers because they were two great big, looked like 5-gallon pails up on the power pole, which was outside their house because everybody's wiring was above ground. So there's going to be more wraps in the primary coil than in the secondary in a step down. So the number of wraps goes down, voltage goes down, current goes up. Step down transformers are used in neighborhoods, cell phone chargers, doorbells to reduce the voltage to the level needed for our electric devices. So this is an amazing little device. That's just simply an iPhone charger. I think the 6 started coming out with these, and everybody says, when those first came out and I picked one up and saw how light it was, I was amazed at that technology. Remember I told you that those step down transformers, so this takes about 120 volts from your wall where it plugs in. It reduces it down, steps it down to about 5 volts is what it's going to actually use for your cell phone or your even your iPad. So that's an incredible. Plus it changes AC current to DC current in that tiny little device that's so light. The old chargers like this were very, very heavy for laptops because they had those big iron coils to do that step down. So this is amazing technology, something again we take very for granted But again, every time I pick one of those up, I'm just amazed that it works the way it does. So let's take a quantitative, meaning we're going to start bringing some numbers into the transformers. So in an ideal transformer, this is straight out of your formula sheet. It's going to show you actually the whole meal deal like that, but I'm going to back it up just a little bit and do one at a time. So our base formula for if you're dealing with the number of turns and the voltage. Number of turns in the primary divided by the number of turns in the secondary is equal to the voltage in the primary divided by the voltage in the secondary. So you notice that on these, primaries on the top, so secondaries on the bottom, and they're the same. Remember, as number of turns goes up, voltage goes up. Number of turns goes up, goes down, voltage goes down. So on the little fraction that we're going to set up this ratio, the P has to be on the top, the P has to be on the top, and the S on the bottom. Now we can take this whole formula and put it upside down. So it could be number of turns in the secondary divided by the number of turns in the primary. But then on the other side, voltage would have to be on the top of the secondary, voltage in the primary on the bottom. We're going to do that today's samples questions. We've got a little technique to help make this a little easier for you to rearrange. But current is the opposite. So now we have the number of turns in the primary. When we look at the top, current has to be the opposite. If it's primary in the top for number of turns or voltage, then current has to be secondary. On the bottom here, number of turns is secondary, so voltage or current has to be primary. And then the third version, again, we have voltage, primary is on top, current always has to be the opposite. Remember, as voltage goes up, current goes down. As voltage goes down, current goes up. So P over S here, S over P for current. So current I will always be different than potential difference V over the number of turns N. So that's that part of it. All right, so let's you can pull out your sample calculation sheets. If you don't have them, not handy, you do have access to a printer. I did send an extra copy along, but hopefully you still have your original ones from the classroom. Makes life a little easier. If you don't, that's okay. Just get some loose leaf paper, some scrap paper, and just copy. It's very important that you spend the time copying these problems down as we go through them, just to get that processing in place. So electricity formulas for calculations, IV, number 4. We're going to go right down here to this section, right here on transformers. So that's what we just went over. Again, N stands for the number of turns. And on your sheet today, I'm going to call them wraps, but wraps are terms. P is primary, S is the secondary. They don't bother telling you V and I because they're still up here, voltage and current. So let's take a look at question number 1. So right away, question number 1 tells us that we're dealing with a step-up transformer. That means that your voltage is going to go from a lower to a higher number, and your number of turns is going to go from a lower to a higher number, but your current is going to go from a higher number to a lower number. So let's go ahead. I think with a set of questions like this, it's probably important to go back to the old squiggly line, write down everything that you know from the question and everything you're trying to find out. So a step-up transformer converts voltage from 12.0 to 120. So that's potential difference. It was the beginning of the question, so that's the primary. This is going to be voltage in your secondary. So write those down. Voltage in the primary, 12.0 volts. Voltage in your secondary, 120 volts. Now, at that point, you want to say, did I get that right? Did I identify those correctly? Said it first. Was that the way the wording was put into place? Again, it's a step-up transformer, so there has to be a higher voltage in the secondary than in the primary. So you can actually do a prediction of this at this point already, because how much did the voltage go up? Went up by a factor of 10. That means the number of wraps is going to go up by a factor of 10. So if we're starting with 20, we can kind of predict that the answer for the number of wraps in the secondary is going to be 200. Let's just tuck that away and let's see where we get. So the second thing it tells you, now the third thing, there's 20 wraps in the primary. So you're going to put N in the primary is equal to 20 turns or 20 wraps. And what are we trying to find out? How many are in the secondary? So we're looking for the number of turns in the secondary. So when you set up these questions, I want you to always do this to make your life easier. Not everybody does this. Some are better than others at rearranging equations. But I'll tell you, your life will be much better if you do this. Always put what you're looking for in your little ratio in the top left-hand corner. So we want to know the number of wraps in the secondary. That's what we're looking for. So that goes in your top corner. Now, n always has to be over n. We're going to find our number of wraps in the secondary using the information from our voltages. So it's going to be V is always going to be over V. So how do we know who's who now on the rest of this? Well, if it's secondary on the top, it has to be primary on the bottom. Voltage and wraps are always the same. So if it's P on the top, it's P on the top. If it's S on the top, it's S on the top. Since the number of wraps is S on the top, then it has to be S and P. Remember, look, when we get to current, that's going to be the opposite. P and S, but it's P and P, S and S. So it's upside down from what we used here. But you can do that with an equation at any time. You can flip the whole thing upside down, provided that you flip both sides. So that's what we did for this equation. Why did we do that? Well, it makes the rearrangement much easier. Now we only have to do a half of a cross multiplication. So the number of wraps in the secondary, number of turns in the secondary, is going to be the NP came up, number of turns in the primary, times the number of turns in the secondary, over the voltage in the primary. Just adjust that a little bit. So number of wraps in the secondary is going to equal number of wraps in the primary, which was 20, times my number of wraps, times my voltage in the secondary, which was 120, divided by my voltage in the primary. Now, if you're good at doing your little math tricks here, 12 will go into 12 once. That means it goes into this 10 times. Number of wraps is equal to 200 turns in the secondary. So 200 turns or 200 wraps. If you would rather use a calculator on that, so we'll just plug that in, 20 times 120, enter, divided by my 12, before I did my cancellation. And again, if you weren't sure of that, there you have your 200 turns in the secondary. So take a few minutes, copy that down, hit pause, and you'll. Question number 2, we're going to deal with a step-down transform. What does that mean? It means voltage will decrease. It means the number of turns will decrease. But it would mean if we were dealing with current, it would go up. But in this case, we're just going to deal with voltage. And again, number of turns. So we'll be dealing with this part of the equation right here. So let's put our little squiggly line in. We have voltage in the primary given as 120 volts. The voltage in the secondary given as 6 volts. It tells us that there's 12 wraps in the secondary. Number of wraps in the secondary is 12. Turns in the secondary. So we want to find the number of wraps in the primary. So again, when you set up your ratio, always put what you're looking for in that upper hand corner. So that's kind of nice. That's our actual form of our equation. This makes it a little bit easier. Remember, P, in this case, is over S. We're dealing with voltage and voltage, so they're the same. P on the top, S on the bottom. We're going to do half of a cross multiplication. So we've got the number of wraps in the primary is equal to the number of wraps in the secondary times the voltage in the primary over the voltage in the secondary. Let's substitute in those numbers. Substituting in, we've got 12 turns in the secondary, 120 volts in the primary, divided by 6 volts in the secondary. And if you punch that into your calculator, you're going to get a quick 240 turns. Now, let's double check in our head to make sure that that's right. We have more turns in the primary than the secondary. That makes sense. Why does that make sense? Because it's a step-down transformer. The potential difference goes down, the voltage goes down, number of wraps has to go down, number of turns has to go down. Okay, we're getting pretty long in this video. It's already up to 26 minutes, so I'm going to just go a little bit quicker. I saw this was a step-up transformer. I did my squiggly. I wrote in my values as they're given. 20 amps in the primary, 20 amps in the secondary, 9 wraps in the primary. So we're looking for how many wraps there are in the secondary. And this makes sense. Look what happens here. The current is going down. It's decreasing by a factor of 10. We divide 20 by 10 to get 2. That's what happens in a step-up transformer. In a step-up transformer, the current goes down. The voltage goes up. Number of wraps go down. So if this came down by 10, we know that this is going to go up by 10, so our prediction would be that it's going to be 90 wraps. But let's go ahead and set up our ratio. So we set up our ratio. We're putting what we're looking for in the upper left-hand corner, number of wraps in the secondary. N over N, we're going to find it from our currents. So S over P. Now remember, we're now dealing with this version of the formula. The P and the S have to be opposite each other. So if there's an S on the top, we need a P on the top for the current. P on the bottom, we need an S. We're going to do a half of a cross multiplication. So we continue over here, do our cross multiplication, half cross multiplication. We end up with N in the primary times I in the primary divided by I in the secondary. Substitute in 9 times 20 over 2.0. And when you punch that in your calculator, if you need to, you're going to get 90 turns, which is what we predicted it would be. So take a couple minutes, hit pause, and catch up on that. So I wrote down my given information and what I was looking for. Read across. It's a step-down transformer, which means that the current goes up. I in the primary was 3. I in the secondary is 9. Number of turns, 20. So since it's a step down, we know that's going to go down. Now again, we can make our prediction. This went down by a factor of 3. We went up by a factor of 3. Multiply 3 by 3, which means this has to go down by 3. So 20 divided by 3, we know 3 times 6 is 18. It's going to be between 6 and 7. So we know that that was all just dumb. I'm not going to forget that. I'm not going to go back and start over again. Let's just move on and carry on. So we've started our calculations. Secondary, we know this has to be S, and this P, that's going to go up. So I did quite a bit there on the pause. I went ahead and wrote my formula out. I rearranged it by half cross multiplication. I substitute in my number of wraps in the secondary was 20 times the current secondary of 9 divided by 3. That works out to 60 turns. And again, so that the fact this is the primary, so this has to go down by a factor of 3. So from 60 down to 20. So that all makes total sense. Hit your pause, get caught up on that. Sorry, I'm rushing here, folks. So now this question is going to deal with our last part of the formula here, potential difference of voltage and current. We read through the question, tells us that the current went from 3 to 1, so 3 in the primary, 1 in the secondary. 10 volts in the primary, what's our voltage in the secondary? So we're going to start that with our upper left-hand corner. So we start with what we're looking for, the top left corner up here again. So the S has to be over a P. Remember, the I's are always opposite. So since there's a secondary, it's a primary on the top. A secondary, half of a quick cross multiplication. So the potential difference in the secondary is equal to our voltage in the primary times current in the primary over current in the. So I jumped ahead kind of quick there. Hit pause if you need to. I did my substitution. 10 volts times 3.0 amps divided by 1.0 amps. That will give us a voltage in the secondary of 30 volts. So again, it was a step-up transformer. So the voltage went up and the current went down. Hit pause and get caught up. So this question is not worded very well at all. And it's a little more difficult because we don't throw the voltages together and then the currents together like we have been. So it tells you started with 120 volts. You converted 120 volts, so that's your voltage in the primary. You converted it to voltage in the secondary of 12.0 volts. So it's a step-down transformer. The voltage went down by a factor of 10. We know our answer should be 50. But let's go ahead. And again, that current, even though it's not worded very clearly, is inferring to be at 5.00 amps in the primary. So we want to find out what is the current in the secondary. So we put down our formula again. I in the secondary is the top left-hand corner. Do a half of a cross multiplication and get I in the secondary is equal to I in the primary times voltage in the primary divided by voltage in the secondary. If you want to hit pause and catch up to that. So I did my substitution. 5 amps times 120 volts divided by 12. Punch that in your calculator and get 50 amps as we predicted. So the voltage went down by a factor of 10. The current goes up by a factor of 10. 32 minutes. Sorry, folks. Have a good one.